So I think it's time we start because we have 10 minutes scheduled for myself or Mauro to do an introduction, I believe, at the beginning, according to the schedule.
Okay, so Susan, the floor is yours. I introduce you, Susan Conway, Vice President of International Association of Geomorphologists. The floor is yours.
Thank you very much, and welcome to everybody. It's a great pleasure to welcome you to this webinar in Central and Eastern Europe, and it's part of International Geomorphology Week that's going on all this week, and you're welcome to attend on any of the other events. I'm just going to share with you briefly a short presentation about, just to introduce a bit the activities of the IAG and about what we've been doing over the last few years in terms of reaching out to you, our community and national scientific members. There's two upcoming events I want to make you aware of that the IAG, not just this International Geomorphology Week, but we have two in-presence meetings that will be coming up in Mashhad in Iran and the International Conference in Coimbra. So the Mashhad Regional Conference was postponed until 2022. And we'll announce that date when it becomes available. Local organisers are arranging that. There's the International Conference in Coimbra coming up in September 2022, postponed from this year. And so I would welcome you for that meeting, which will also include, so don't just keep that week free. There'll be field trips scheduled for both the week before and the week after. So make sure you put sufficient time in your diaries to attend that conference. And I just wanted to make you aware that if you weren't aware of this, that the IAG can actually help you support your events. So we organize, as I said, this International Geomorphology Week, but also the regional and international conferences. But we also want to support your events on geomorphology around the world. And so we can provide auspices to support your meeting, enabling you to advertise it via our website and social media. We can offer grants for young geomorphologists to attend your meetings. So if you want that to happen, please just get in touch. Another way that you can contribute to the IAG is to actually propose your own regional or international meeting, and that will be welcoming proposals for those two sorts of conferences in Coimbra next year. So if you're thinking that you'd like to host one of these conferences, then please get in touch with us and we can tell you how to go about preparing that bid. So if you're not aware, hopefully you are because you're signed up to this webinar, you can find out all the latest news about the IAG at our website, which is shown here. But also please don't forget, and please sign up to the Geomorph list. This is an email list server where anybody can actually post announcements, so job adverts, conferences, PhD opportunities, a new book that's come out, anything like that. You can post this list. It's open to everybody, and it's for the benefit of the whole geomorphological community. So please, if you're not already signed up to Geomorph list, sign up and receive all the latest news from the geomorphological community. You can also follow us, the IAG, as well on Facebook and Twitter. So just see our website for how to do that. We also have memorandum of understanding with various other societies and associations, which means that we work with those other associations and societies to both co-organize sessions and meetings, but also to contribute to different events. So have joint grant schemes, for example. So we're not just working alone, we're working with the whole sort of geoscience community to try and bring geomorphology to the fore. So this is International Geomorphology Week, and it was established last year, and due to the COVID crisis, unfortunately, the activities were somewhat smaller than we were hoping for, but there were activities that went on, notably here in Central Europe as well. And this year, it's different. We have lots of things going on all week, and this webinar forms one of those fantastic events. Bear in mind, there's also some events next week, because International Women's Day is Monday, the 8th of March. And so there are a couple of other extra add-on events that are going on next week. So please, it's not all over. Have a look. 2022, what will you do? If you have any ideas of events and things you want to do, please get back to us. Please let us know what you liked and didn't like about this week as well. Another thing I don't know whether you're all aware of is that the IAG also has a network of young geomorphologist groups. And we're always aiming, we always want to encourage young geomorphologists, early career scientists to form these groups and get together and do things. So if you're a young or early career geomorphologist and you're not in a group and you want to be, or you're not in a group and you want to form one, we're here to help, so get in touch. The other point is for both early and later career scientists attending this meeting is that the executive committee, as it stands now, renews every 4 years. So at the international conference in Coimbra, there will be elections for new committee members to join the executive committee. And so if this is something you might be interested in, or you don't really know what it involves, please get in touch. We can tell you about what that work involves, and we do encourage everybody from the community, anyone who is passionate about geomorphology, to come and join us and get nominated by your national scientific member. And so I'm going to stop there. I don't know if Mauro has joined us or not, but
yes,
he has. Maybe he'd like to say something. Maybe he'd like to add something to what I've said already.
Okay, thank you very much, Susan. I kindly ask Mauro, the president of the International Association of Geomorphology, Mauro Soldati, to address to the participants.
Okay, now I can, because I didn't have the privilege to reactivate my audio, so it was saying that the host should have done it. Okay, so welcome everybody. Thanks to be here with us today. I hope you have joined the previous events of the International Geomorphology Week, and that you are attending also new ones today, later in the day, or in the next days. Our Vice President, Susan, is modest enough to avoid saying you that it has been really successful, because she's actually the one who coordinated the whole stuff, and we've been having very large numbers of registrants and participants as well. So this went beyond actually our expectations. This doesn't mean that we don't want to meet anymore in presence, because it is our must to have our conferences and field activities, field trips, intensive courses on the field, because we are geomorphologists and we really need this. But we have learned how to meet and how to reach all parts of the world through these webinars and activities online. So we will probably take into consideration this type of liaising with national scientific members and geomorphologists in general, also in the near future. This morning we had a very successful meeting, which is still ongoing, involving the network of young geomorphologists that was mentioned by Susan, and the Polish young geomorphology group and the Romanian young geomorphologist group presented their activity, and I really invite, as Susan did before, young geomorphologists from other countries that are affiliated to the IAG to form a group within their countries. These groups, of course, have to be strictly linked to the national bodies that are affiliated to the IAG. but they should not be formalized. Actually, they can be set up on an informal base and collaborate and liaise with the network, which is actually doing very, very interesting activities. So that's all from my side. I wish you a pleasant participation in this event, and I would like to thank the coordinators, Piotr Migon and Mihai Miku, for organizing this event, and Konstantinos Vouvalidis to hosting it today. So thanks really, Konstantinos, for your support.
Good afternoon, everyone. I'm very glad to be here and have an opportunity to present our study inside such a large community. And today I would like to share some results of our multi-temporal and multi-approach study of interfluvial landscapes of Central European uplands. Today I present the results of work of a large group of scientists from Moscow State University, Department of Geomorphology and Paleogeography, and from Institute of Geography of Russian Academy of Science. Today I would like to put some emphasis on the relationship between the glacial heritage and postglacial metamorphosis in the modern landscapes of those uplands. And today I'd like to focus on one of those uplands that is located in the middle of the marginal zone of Moscow, or late Zaalian glaciation, last for this territory, and which was forming here after that by postglacial processes during last 120K. If we look on the state geological map of Russia, of this territory, we will find here typical end moraines and end moraine plains with hilly landscapes. And if we turn to the geomorphological structure of this area, we will find that the contours almost completely repeat those of quaternary geology contours, showing that mostly this region in the basin of Volga River, in the upper Volga River, and in the basin of the smaller catchment of Narrow Lake Basin, is completely determined by the action of by the accumulation of moraine sediments. However, our study concentrated on the northeastern part of this upland, and we applied different approaches and multi-scale approach to combine the info about the lithological structure, about the geomorphic landscapes, and about pedogenic and cryogenic processes that formed these landscapes to the modern look. The typical landscapes of this area you can see on the slide, and they're shown as a marker slope of this upland that's gently rolling down to the Narrow Lake Basin, which is actually only 200 kilometers from Moscow to the northeast. And here you can see several gullies and small valleys that incise this slope with some large interfluvial areas that surround them. And here you can see the famous, at least in Russia, one of the most famous reference sections called Geomorphometric with different letters, which were studied since the beginning of the last century, and actually focused on the structure of the sediments that were exposed in the gullies sides and actually exposed the interglacial pits of the last interglacial and the sedimentary cover of the late Pleistocene afterwards. The studies re-emerged after the second half of the last century in 21st century and provided some stratigraphic and chronological constraints on this territory. However, better dating showed that a lot of hiatuses occur here in these reference sections, so that turned us to look further around these classical sections and to look at the interfluvial landscapes. And here on the most part of the territory, gently rolling flat or slightly undulating surface occurs with several superimposed structures and landscape forms. And the most typical of them are large flat-topped hills that are very prominent and dominate above the territory in the upper interfluvial level. However, the most part of the territory is covered by also small round-topped hillocks of smaller size and height, and those two positive landforms are submerged by either linear depressions of a greater size or by smaller closed depressions with flat bottoms and relatively steep slopes. After this brief introduction to the geomorphological structure, I would like to turn to the geological interior of those landforms to better understand how this territory was formed. So in the upper interfluvial level, the structure of those, the largest hills at this territory are a typical limnocames, which show some transition from deep water limnoglacial facies to the more shallow water glacial lacustrine facies with some input of debris flows, subaquatic debris flows, and that show different types of textures and deformations of scene and post-depositional character. So the smaller hillocks are usually represented by, composed by sands of glaciofluvial genesis mostly, or by undetermined basin facies of glacial till or glacial lacustrine stratified sediments mostly, and can be with some constraints referred to as moraine, typical moraines. However, they are not really typical for this territory. And the most part of the background plane is covered by small cover of redeposited moraines and underlaid by also by those sandy deposits of glaciofluvial genesis. And the lower part of the background plane is usually presented by the glacial lacustrine sediments, but of another of more younger time and of more of worse sorting and a lot of deformation caused by during the sedimentation, and can be interpreted as a terrace of a larger supraglacial basin. So as you can see, the typical basalt tills or moraines, they are not really well represented on this territory, and we find them only as inclusions in glacial lacustrine sequences or in the bottoms of most the deepest incisions, and they do not provide that much geomorphic evidence as it shows on the geological maps. For this part of the research, we can show this kind of sketch of a geomorphological map. It's a preliminary version, but it shows the main distribution of major landforms of late Moscow landscapes. And besides the ones I already mentioned, there are a lot of linear depressions with those were filled later during the postglacial, and at that time that appeared to be kettle hulls appeared due to glacial-karstic processes. So if we turn to the structure of exactly those sediment traps or landfills, we will see that more than 10 meters of such postglacial sedimentary cover can be found there, and it should probably somehow differ the actual look of modern landscapes from the ones that we could have seen at the late glacial time, at the late Moscow time, sorry. And the structure of one of those kettle hulls is shown on this satellite shot and shows the sequence of pits at the bottom and upwards a large sequence of laminated stratified sediments of lacustrine origin with different types of and generations of lamination, and with a tendency to more colder and drier conditions from bottom to the surface. Here we have some signs of cryogenic reworking and some age control that shows that the middle part of the sequence was formed during the Nis 3 stage, during the middle Valdai time. However, it was going from the last interglacial until the transition to Holocene, almost with the prolonged lacustrine sedimentation. Here is just a sketch of this infill of such kind of a kettle hull, which shows that this sequence of 10 and more meters severely changed the relative elevation of this territory and actually changed the structure of geomorphic processes that were going on the surface of those landscapes. In the linear depressions, we see almost the same type of structure, of geological structure. However, we can find here some hiatuses and erosional events that have sometimes disposed some parts of the geological record. However, we see the same sequence of events and the same sequence of sedimentary environments in this type of depressions. And the age control is almost the same, which puts it in between of the Mikulina pedogenesis, in last interglacial pedogenesis, and modern and transition to Holocene from the late glacial. if we return to the more classical sections of this gullies that were studied for the last 70 years here, we actually find the same sequence of events, however, with much more considerable role of erosion. And here some parts of lacustrine sediments are eroded and either redeposited in alluvial environments, either just gone. And you can see here some signs of cryogenic reworking of this territory. So if we look at the most whole, the entire sequence that we found in this region, we will see that here are always on the base of the glacial lacustrine or moraine sediments, there are some geysers and pits of last interglacial, covered by specific sequence of lacustrine and slope sediments till the late Holocene slope sediments, with some action of human-induced erosion and natural erosion events that are recorded in the sequence of pyrogenic redeposited sediments. And if we interpret this in the geomorphological way, we can see that the direction in which the incisions were growing during this time were different in the early pleniglacial and in the late glacial time. So the geomorphic structure of the territory changed a lot during this period. And the last object I would like to pay your attention to is the foothills of such great large hills, where you would expect to have very stable environments. However, very large, very thick sediments of colluvial origin appear here, and we can distinguish at least three main colluvial levels or units here, which are penetrated by different generations of cryogenic ice wedges and ice wedge casts. So we can see that the late glacial landscapes were already severely changed by the slow processes during the early Holocene and middle Holocene time. And so we can show this some kind of this reworking during the postglacial time in the changes of environment and in the changes of landscapes on our geomorphological map that shows that the middle parts of the interfluves have undergone a severe transformation during the postglacial time. And so I wouldn't stop on the detailed legend and just go straight to the main implications of the work. The first one would be that initial late Moscow or late Zalian landscapes has mostly limnoglacial origin, with different types of sedimentation cause different types of landforms. Secondly, the role of moraines in modern landscapes of Bergslags Upland is overestimated and in general severely subdued to glacial lacustrine sedimentation and geomorphic processes. The third one would be that initial elevations of those limnoglacial plains caused the major alteration of postglacial geomorphic processes and deposition. So the late Pleistocene geomorphic processes have caused the main redistribution of the sediments during this time. And the last ones are that if we look precisely on the interfluves, we will see that the two main geomorphic agents of postglacial transformation were lacustrine sedimentation, and it was followed by significantly intensified slope processes. And both of them caused severe transformation of the topography and of the terrain. Here I would like to stop and thank you all for the attention and for the opportunity to tell you our research.
Thank you, Konstantinos, and I would like to thank the IAG for having the opportunity to present the morphodynamics and flow interactions of deltaic wave influence river mouths, which was a study which was part of my PhD that I finished recently. And you will see here a video of what is the southernmost branch of the Danube Delta, is the St. George River and the river mouth. It's during floods at this moment, and it releases massive quantities of sediment that are transported by the turbulent river jet and the river plume into the sea. You can see the contrast here in color. And after that, they are dispersed downdrift over what is a barrier island in the distance. And we started a few years back by taking lots of cores and dating them with carbon-14, also taking optically luminescence samples to find the ages of the sands and sediments. And at the end, we arrived at this evolutionary model of the Danube Delta, which spans the last 7,500 years. So basically, the Danube Delta started forming into an embayment. When it reached the open sea, different lobes, depending on the higher sediment transport of that particular river mouth starting developing. And this interaction between the river mouths and the waves in the Danube Delta and in all the wave influence deltas in the world basically impose the architecture of the delta and the erosion retreat rates of particular stretches of coast. So understanding river mouths and their morphodynamics, even in the present, it's very important, either in explaining past changes or in trying to predict what will happen in the future. At the present, most of the large deltas are in the red. They are eroding. You can see here a distribution of deltas that are eroding in the world. Only pristine river basins at the moment carry sufficient sediment to sustain deltaic growth. Fortunately, Danube Delta erosion seems to be balanced with accumulation. And worldwide, this is due to what was named a pandemic construction of dams. So this pandemic actually, which started in the last century, affects sediment delivery to the river mouths. And if you have less sediment to be available and being redistributed along shore, then you have more erosional problems. Now moving on to the study area, you can see St. George here again. Basically, the morphodynamics here, it's influenced by the external factors, which are the storms occurring in the winter and floods usually in the spring. And you can see in this animation that that river mouths are quite dynamic geomorphologic entities, are one of the most dynamic in the world actually. And we use a lot of data in this study, starting from bathymetric measurements with a sonar on a 4x4 kilometer grid. You can see here the mouth of the St. George with a river mouth bar. This is what this landform is called. It's asymmetric because it has this crest that is attached only on the one side. And we measure successively and in the last 15 years. And here you can see the difference in elevation models. With red is accumulation in our case, and with the blue is erosion, and you see quite a lot of variability. And from these elevation models, we can derive the volumes. Also, we use flood discharge data, wave height data. And here you can see an overview of the Danube Delta coast. St. George is here in the south. Waves are coming from the northeast, according to these wave rows, and they impose this longshore circulation transport pattern. It's with, you can see here the arrows in yellow. So in front of the river mouth, we have about 1 million cubic meters of sediment circulating each year. And different points where wind data, discharge data are available. We use current measurements done with an ADCP in front of the river mouth. And a numerical model in order to simulate hydrodynamic conditions during floods and storms. And this is by DHI model. It is based on the Reynolds average Navier-Stokes equations, and is able to simulate most of the important processes like wave refraction and diffraction, which are important in this kind of river mouth environments. You can see here the model mesh that was constructed. And first, we run some simulation at what you see here, the river mouths of the Danube, starting from the river mouths of the north, and down here the river mouths of St. George. On the left, there are the salinity fields, and on the right, the current fields. On the bottom is the wind speed, and you see here the wind vectors directions. What is important are these events that are now starting. This is a southern wind, which imposes an upwelling type of river plume, which means that the plume is a bit more detached and going offshore. Here also with the southern wind. And at the end of this simulation, we'll see a northern downwelling wind that will basically create a longshore current, continuous alongshore current, with a plume that is that sticks more to the coast. Here are some drone photographs that show what this type of circulation looks like. So after the river jet enters into the sea, it transforms into this buoyant river plume, which is deflected by the Danube coastal current. And we use some measurements. This is the river mouth bar. On top, you will see velocities between the model and the measured. The agreement between the data is quite good, and so we use it as calibration. The agreement between direction is okay also. What we see here is the river jet, which exits the river mouth, saline intrusion inside the river mouth, and the Danube coastal current, which goes from north to south, and possibly a return flow here. Also, we calibrated the model with a few months of wave simulations, and we also arrived at quite good results. So the first result is the flood simulations. This is to understand the processes occurring during floods, with increasing discharge thresholds up to 4,000 cubic meters per second. This is the surface velocity. You see here a cross section, a vertical section on the river mouth. At low discharge, we have some saline intrusion, which you see here with the red inside the river mouth. But with increasing discharge, the fresh water is this point of plume liftoff is located more offshore. And what is interesting is that the recirculation type of hydrodynamics appears to develop. Also on the bottom, you can see the bed shear stress, which is an indication of the erosive capacity of the current. So basically, we will expect erosion inside the river mouth and the position outside where there is no stress on the bed. And this is basically what happens. So inside the river mouth, we have no deposition, and the position occurs immediately after the bar crest and more offshore. So the simulations agree quite well and explain the bed level changes. Next was to simulate the storms, increasing wave height. The wave height come from 45° northeast, from 1.5 meters up to 6 meters, which is what we expect during extreme storm conditions. We see the developing of a longshore current, quite a strong one with increasing wave heights. You can see here a cross section of vertical section of this longshore current. The wave refraction patterns, the height and direction, and this time the bed shear stress is located mostly offshore the river mouth bar crest. And we expect erosion actually in this area during the extreme storms. And this is what happens and what our measurements revealed. Now, after we know the processes and what happens during particular conditions, it's interesting to look at the time series of the volume changes, which you see here on the bottom, and flood and storm data. So basically, is what we see that during high discharge we get deposition, and during some particular years, like here in 2012, we see a high erosion, which went down to 6 million cubic meters during that particular year. So we came up with a flood storm index, which is based on the ratio of the duration of floods and storms at the river mouth of the St. George, and this is based on percentile approach. So a duration of discharge above 75th percentile, which equals 2,200 cubic meters per second, over the duration of waves of 98th percentile, which is 2.5 meters. And in this graph, you see this flood storm index, which in this case is based on duration, and the changes in volume recorded at the river mouth. So basically, we get an R-square of 0.8, which is very good. So our measurements in volume change overall agree with this storm flood index. And here are different thresholds, both of discharge and of wave height. And we basically picked like the intersection for the highest correlation of both thresholds. And what this threshold also tell us is that for every hour of storm over 2.5 meters, we basically need 15 hours of floods above 2,200 cubic meters per second discharge in order to maintain the river mouth with a neutral sediment budget. So if you have more storms than this, then we will expect erosion, and if we have a higher duration of floods during that particular year, we will expect deposition. Here, this storm flood index is computed based on sediment thresholds and wave power, and we see like the same good agreement, even a better agreement. But also, this duration is quite intuitive and interesting to think about. So the conclusion of the first part are that floods and storms drive morphological change at the river mouth. And you can see here a conceptual model which basically resumes our simulations and our data measurements. And the new proposed index, the flood storm index, based on storm and flood thresholds, explain the sediment budget variability at the Sfântu Gheorghe river mouth. So although this particular index will not apply to other river mouths exactly, like we expect that the basic processes and the basic balance to be maintained in other world river mouths. And also this linear response in bathymetric change is important, because river mouths are considered to be are infamous actually for being very complex environments. And now let's move on to the next part, jet and wave-driven lockshore crane interaction at the river mouths. You see here a simulation of increasing discharge and with a storm with waves approaching northeast. So this is what the circulation results in these extreme conditions. So you can see here a selection of river mouths worldwide. These are like medium to large river mouths, wave influence, not that much tides. Overall in the world, there are about 2,200 deltaic river mouths which have been recently identified. And based on the images on the bathymetrical models we have for the Rhone and for St. George, we constructed 5 idealized river mouths, a river mouth without a mouth bar, and a few cases with mouth bars. First, large mouth bars with a coast at different orientation to the mouth bar. These are symmetrical, whereas we also opted for the use of an asymmetrical mouth bar, which is the one in St. George, as you see here on the bottle, and a small symmetrical mouth bar as well. And we use 5 different wave height thresholds from 0.75 to 6 meters, 5 different directional thresholds, and 5 river discharge thresholds. In total, 650 different conditions were modeled. You can see here the basic circulation of either discharge, river discharge, which results in this jet circulation, which is like a candle type, and the wave-driven circulation, basically on the same bathymetry, but this time we cut off the river jet, and we are left only with the longshore current. But we don't know how it looks when these interact on the different thresholds. And what you see here is some simulations with the river jet at 0, different directions. So 90 degrees means that waves come directly perpendicular to the shore, whereas 0 degrees are completely oblique, and 45 degrees are inclined. And the largest velocities in the longshore current we identify occur with increasing wave height and around 45 degrees of wave direction. And with increasing jet discharge, basically we see that the jet is not that much affected here at 1,000 cubic meters per second with this low wave height, so 0.75, 1.5 meters. But with increasing jet, we see that the longshore current in this increasing wave simulations are also diverted. So, and this is the maximum that we use, 8,000 cubic meters per second. And we arrived at at these graphs, which show the jet deflection angle. So basically, for each simulation, we took an angle of the jet deflection, and we try to compare it with a simple measurement of momentum balance, which is the momentum of jet over the momentum of waves. And this seems to explain, so when this balance is around 1, it means that the forces are in balance, and actually the jet is deflected 45 degrees. Also, this can be more easily conceptually, we can have a better intuition if we use discharges. So if we have an equal discharge of the jet and of the longshore current, we get a 45-degree deflection. And with increasing discharge of the jet, for example, we have a straight jet, and with increasing discharge of the longshore current, we have a more deflected jet. So basically now we have also the theory of what happens in jet deflection. And in case you're wondering, straight jet like that do occur in nature. So this is a maintained river mouth in the central Danube Delta branch at Sulina. So basically, we have no mouth bar here, and the river debouches directly into the sea without a mouth bar. And at the St. George, even these measurements can be applied, and we can use them to maybe interrogate the possibility of the jet deflection and when it will occur. In nature, though, rivers have mouth bars, and they impose a very complex circulation type. So here you see the same threshold simulation, but this time we have a large mouth bar. We don't have any jet, but the mouth bar imposes some divergent currents, because here, for example, the waves come at 67.5 degrees. They create the divergent currents on the mouth bar, which interact with the longshore current. And with increasing discharge, we get a higher deflection sometimes. This will be published in a recent paper. So the conclusions are that direct jet and longshore current interactions seem to be predictable and dependent on balances of momentum, and the river mouth bar morphology may regulate jet wave interactions. I invite you to look at this publication, which we managed to write recently, and please visit my ResearchGate profile also. And would like to thank everyone who contributed to this work, my co-directors, PhD co-directors, and the colleagues at the St. George Marine and Fluvial Research Station. Thanks a lot.
Thank you very much. It is a great pleasure to be a part of this seminar. Thank you for this opportunity to share my work with others and to show you how interesting sandstone's geomorphology can be. I titled this presentation Geomorphometric Characteristics of Cleft and Valley Systems, Insights from Studies of Valley Network in Sandstone Tablelands, but probably I should add of Elbe Sandstone Mountains, because this is the place where I would like you to take you today. But first, let me please introduce myself. I am a PhD student, somewhere at the beginning of my scientific career. I am a PhD student at the Department of Geomorphology, Institute of Geography and Regional Development, University of Wrocław in Poland. During my bachelor's and master's degree, I carried out projects in geoarchaeology. I also had an opportunity to work in the research group led by Professor Piotr Migoń, who is my supervisor now, where we dealt with paleolandslides recognition, but also geodiversity and geoheritage. At that time, I got to know the specifics of working in sandstone areas, which confirmed my belief that I sold my soul to geomorphology. So let's take a look at what our field work looks like. Like every work, it has its ups and downs. Sometimes you have to work regardless of the weather conditions. Most of the days you work for 10, 12, or even 14 hours per day. You have to carry heavy equipment, traversing steep slopes. This case is especially true with geophysical research like ERT. Here I would like to mention Dr. Marek Kasprzak from our university and Dr. Filip Hardwig and other colleagues from Institute of Rock Structure and Mechanics, Czech Academy of Sciences, who often share that effort with us as part of several years of international cooperation between our research centers. Working in the field gives a lot of joy and a lot of satisfaction, especially in such a complex and mysterious terrain of sandstone-dominated areas. Although I love to work in the field, today's presentation will show you the first results of my desk work. As the geomorphometric analysis with use of high-resolution digital elevation model is major part of my work. But first, let's indicate the objectives of this research. Scientific potential of sandstone-dominated terrains for resolving fundamental problems of geomorphology is often underlined. Nonetheless, sandstone landscapes seem under-researched compared to vast output in granite or even karst areas. Corollary to that are deficits in established methodology, which can be followed. Erosional topography in sandstone tablelands is typified by a range of distinctive landforms, which combined into complex, extremely rough relief. This peculiarity, both at the scale of individual landforms as well as larger tracts of relief, can be demonstrated using geomorphometric approach, hardly employed in this setting so far. In this way, different sandstone terrains may be compared with one another, and similarities and differences may be evaluated quantitatively, creating ample opportunities for future research and comparative studies. And that is why I set myself a goal of the development of a methodological approach that can be widely used for morphological comparative analysis of valley network in sandstone-dominated tablelands. Today's presentation is based on the example of Elbe sandstone mountains that are located on the border between the Czech Republic and Germany, about 40 kilometers southeast of the city of Dresden. It owes its existence to the extensive presence of flat-lying Upper Cretaceous sedimentary rocks. Lithologically, the area is dominated by sandstones. The canyon of the Elbe River divides Elbe sandstone mountains into two regions of contrasting morphology. The southern and western part, south of the Elbe, is dominated by residual tabular hills of all kinds, including mesas and buttes. The part east and north of the Elbe is mainly a heavily dissected plateau with a labyrinth of minor canyons, gorges, and ravines cut deeply in the ground, which can be seen at the photo on the right, where you can see the main forest scale. The area with these majestic hills on the left side of the Elbe River and labyrinths of canyons on the right side of the river is of interest of scientists from various specializations, mainly geoarchaeologists. But in recent years, several articles have been written on the geomorphology of the area. In one of them, which appeared in Geomorphology, I had the pleasure to be a co-author. With this emphasis of research so far on convex forms, it is time to delve into the nature of concave forms. 4 morphometric measures will be helping me today: slope, valley depth, topographic wetness index, and morphometric protection index, which will be discussed in examples. As for the examples, this will be 2 cleft and valley systems located in 2 different parts of the plateau. Sandsgrund, located on the edge of the plateau, and Webersschluchte, located in the central part of the plateau. Please note that the plateau extends over the Czech part of the Elbe sandstone mountains, which this image does not take into account due to lack of elevation data, which will be purchased, I hope, one day. Those cleft and valley systems are composed of minor box-shaped valleys with the morphological character of gorges and canyons, often dry and channel-less, but nevertheless deeply incised. Let's take a closer look at them. Sandsgrund, which is lying in the marginal part of the plateau, consists of 1 main valley, 2 or 3 minor valleys, and an extensive system of clefts, especially in its eastern part. Webersschluchte is about half size of the Sandsgrund basin. The slope inclination, about 60 degrees, separates main valley by high, steep rock cliffs. Valley depth is calculated as a difference between the elevation and an interpolated ridge level. On the Sandsgrund example, we can see how clearly these minor valleys are cut into bedrock. There is also a clear difference between the section of western and eastern side of the Sandsgrund Valley, while in the cleft and valley system of Webersschluchte, both sides of the basin are similar in the context. Both are strongly dissected. Topographic wetness index is a measure widely used in hydrological modeling to identify areas likely to contribute surface flow, which is extremely helpful here while working on the areas with no permanent drainage. High values, here in blue, shows lines of water runoff, which can be better seen when we reclassify raster to standard deviations. Then those tracts of relief can be seen more clearly. 2 last images present topographic wetness index values above its mean, +1 and 2 standard deviations. Example of Webersschluchte system of highly dissected terrain is even harder to interpret water runoff pathways. Let's look at reclassified values, which are great help to reveal structural connectivity in this extremely rough terrain. The last morphometric measure I would like you to see today is morphometric protection index. It is found to provide valuable insight into the nature of concave landforms and their diversity. Here you can see some photos of the terrain. As you can see, very, very deep and narrow. narrow concave forms. The morphometric protection index approach represents the diversity of valley depth and width along the longitudinal profile, which we can see over here. As you can see, the black line is a topographic longitudinal profile, and the red line are values of morphometric protection index. The sections with high values of MPE of this morphometric protection index are very deep and very narrow sections with the bottom poorly represented by the digital elevation data. To help myself with this additional cross profile, which we can see in the one of minor valleys of the Sandsgrund system. This valley is called Lattengrund. I presented here four cross profiles. The first one, in the upper part of the valley, we've got headwater ravine. Next, box-shaped valley. The other cross profile present slot canyon and the box-shaped valley again. Let's see how it looks with Weber-Schlichter. Morphometric protection index values above 0.6 precisely show narrow clefts and help to evaluate the degree of plateau dissection. Again, some photos. Here is Weber's Grütte, so Weber's cave. There were a small waterfall inside the cave. Something which looked like V-shaped valley. Oh, sorry. And box-shaped valley. Here we can see that the section poorly represented by digital elevation data are very long. It takes almost half of the length of the valley. For topographic profiles, again in characteristic points, presented over here on the example of one of minor valley of Weber-Schlichter system. At the upper part, we've got headwater ravine again. Next profile present asymmetric valley, slot canyon, and wider canyon as a for cross profile. Those changes are, as you can see, on very short length of the valley, because it's just 450 meters long. And that changes of shape are very interesting in terms of, from the point of view of genesis of a valley network and the drainage of the area. To conclude, longitudinal profile and topographic cross profiles depict morphological change along canyons. In regularly jointed sandstone grid-like patterns of passageways between bedrock elevations originate, difficult to analyze using conventional measures pertinent to drainage networks. Morphometric protection index analysis found to provide valuable insights into the nature of concave landforms and their diversity. High morphometric protection values narrow and deep sections which tend to be poorly represented by digital elevation model and point to places which may need additional help of field visit to describe morphology of the section and provide more detailed geomorphological mapping. DEM attributes such as topographic wetness index reveal structural connectivity patterns in rough sandstone terrains. Furthermore, differences between structural and functional connectivity were demonstrated. The latter occurs rarely, and there are only a few permanent sediment transfer pathways in the test areas, while valley morphology is clearly identifiable. That's how my work hypothesis occurs. I hope I will verify it in my future research. The presence of deeply incised valley network with underdeveloped stream system, boulder-filled canyon floors, and numerous sinkholes allowed one to hypothesize that underground drainage is a very important but overlooked factor in the morphogenesis of sandstone areas. And that would be all for today. Thank you very much for the attention.
Okay, hello. Can you see my presentation?
Of course, you can proceed.
Okay, so good afternoon, everybody. My name is Kacper. Thank you for the opportunity to talk today. I would like to give a presentation about recent development of a windy glacier, glacial marginal zone, and maritime periglaciation, so Shetland Islands, Antarctic. Contemporary retreat of glaciers is well visible in the West Antarctic region. The aim of this study was to evaluate the development of windy glacier foreland, which recently turned from tidewater to land-based, and to infer about glacial dynamics and local periglacial environment. The research was based on photointerpretation of a high-resolution orthophoto map and a digital elevation model. The geomorphological map obtained includes 31 types of landforms and water bodies. And I studied at the University of Warsaw in Poland at the College of Interfaculty Individual Studies in Mathematics and Natural Sciences. And I want to say big thanks to Professor Maciej Domski and Dr. Anna Zmars, who helped me during this study. They worked at the Faculty of Geography and Regional Studies at University of Warsaw. And Dr. Anna Zmars were at Polish Antarctic Station and coordinated the whole survey on King George Island. The area of this study is located at King George Island. It's the largest of the South Shetland Islands, and it's approximately 1,150 square kilometers. It's about 120 kilometers from the Antarctic Peninsula. The group of South Shetland Islands consists of 11 major islands. And what's important in this study, over 90% of the island's surface is permanently glaciated. The area of this study is on the south coast of King George Island, about 10 kilometers from Henryk Rostowski Polish Antarctic Station. The analyzed surface is the Windy Glacier foreland and the Red Hill slope. To the east from this terrain, there is an Antarctic specially protected area 1.56 square kilometers. King George Island lies in a polar maritime climate. It's characterized by highly dynamic weather conditions. The temperature is highly variable, with mean annual air temperature minus 1.5 Celsius degrees. And between 1948 and 2011, the temperature increased by 1.2 Celsius degrees. But since the beginning of the 21st century, we observed a slightly negative temperature trend, which reduced the glaciation process. There is a lack of permafrost near the sea level, and the wind is very often over 100 kilometers per hour. The unmanned aerial vehicle beyond visual line of sight means that the operator loses the aircraft from the horizon. The flight was autonomous, but at any time it could be interrupted by sending the order to return to the base. Photogrammetric survey over Windy Glacier foreland and Red Hill allowed for elaboration of a high-resolution orthophoto map and digital elevation model. The images were taken in November 2016, and the unmanned aerial vehicle was designed especially for polar, very windy conditions and manufactured in the University of Technology. The flight path lines were spaced about 70 meters apart. The flight altitude was about 500 meters above sea level. In total, there were 3 flights that took 7 hours in total. The covered flight distance equals 720 kilometers. And then those images were used by Dr. Anna Zmars to create orthophoto map and digital elevation model. The resolution of orthophoto map is 0.06 meters, and resolution of digital elevation model is 0.25 meters. I based also on Rafał Pudełko topographic map and Google Earth images. And on the west part of the study area is well visible Red Hill. Its highest point, it's over 120 meters above sea level. The south slope ends with about 30 meters, and to the east the terrain inclines gently to Windy Glacier foreland, which is recently deglaciated, and it's a very flat surface with 2 big glacial lagoons. And Windy Glacier flows from the Warszawa ice field. Ice thickness in the frontal part does not exceed 100 meters. And as we can see, till 2006, most of the analyzed area was under ice. Only the Red Hill and Patelnia Point were not glaciated at this period. Because of increasing temperature, the front of the glacier retreated 409 meters in years 1979 and 2016. It gives about 11 meters yearly. And what's important, Windy Glacier turned from being tidewater to land terminating. So calving, which is the most effective process of ablation, was stopped. And due stopping calving and a slightly negative temperature trend since the beginning of the 21st century, the glaciation got lower in recent years. During mapping, I recognized 31 types of landforms, and I grouped them into 9 groups that you can see on the right side. The chart presents the area of particular groups of landforms, and as we can see, water bodies take 23%, and it's determined by 2 large glacial lagoons. Other large groups are fluvial and fluvioglacial landforms and littoral landforms. And 60% of the area is not recognized because there are not enough. Sorry, I think that there were
there was a problem with your connection. Don't worry. Share again.
Okay.
Maybe if you turn off the camera, the transfer of data will be better.
And what was the last chart that you've seen?
With the pie chart, when you describe the groups of the landforms.
So here, yes?
Yes, yes.
And now everything works?
Yes, everything works. Start from this slide.
Okay, thank you. So during mapping, I recognized 31 types of landforms, and I grouped them into 9 groups. And the chart presents area of particular groups of landforms. As we can see, water bodies take 23%, and it's determined by 2 large glacial lagoons. And 16% of the area is not recognized because there are not enough attributes. And on the basis of orthophoto map and digital elevation model, I mapped the terrain and created the geomorphological map that I present on this chart. I manually vectorized the area based on photo interpretation, and high resolution allowed mapping also very small landforms. Red Hill was not glaciated since 1979. And the area of the scarp is subject of intensive periglaciation with well-developed solifluction landforms and sorted pattern ground. The frost sorted structures look active due to the lack of vegetation. Red Hill slopes and scarps Red Hill slopes end with scarps and talus slopes. In front of the Windy Glacier is an area that was deglaciated after 1979. It's dominated by ground moraine with small recessional moraine ridges. Between 2006 and 2016, the glacier deposited a well-developed patch of fluted moraine with small drumlins. Fluted moraine contacts directly with the glacier, and the distinction between small drumlins and flutes I will talk over in the next part of my presentation. The area is dotted with erratic boulders, some exceeding 1 meter in diameter, and dissected by river channels up to 15 meters wide and 6 meters deep. And most of them were dry during the photogrammetric survey. There is no visible terrestrial little ice age terminal moraine ridges because the glacier terminated in the sea in the Little Ice Age maximum. The oldest end moraine complex, recessional moraine ridges, are recognized at Patelnia Point and should be associated with the 20th century still stands or short advances. 2 narrow laterofrontal moraine ridges are developed, one along eastern upper edge of the glacier floor, and another one at foothills of taluses deposited on the eastern slopes of Red Hill. We can determine a glacial periglacial transition zone. It's appointed between the lowest limit of periglacial and the upper limit of glacial landforms. So it's between 64-76 meters above sea level, and it's marked Figures A, B, and C show in order sorted polygons, sorted stripes, and solifluxon sheet, or are located at the red hills or over 70 meters above sea level. Next three figures show different landforms on windy glacier foreland. And here is the moraine, ground moraine, where you can see large erratic boulders. Here is a recessional moraine ridge and fluted moraine with well visible long flutes and erratic boulders as well. And as we can see, it contacts directly with the glacier. Distinction between flutes and small drumlins is based on length to elongation diagram. More elongated landforms being treated as flutes, and in most cases elongation ratio for flutes is higher than 5. We have observed two semi-separate swarms on the length to elongation ratio diagram. It allowed us to draw a line boundary between the small drumlins and flutes. As you can see, very helpful was also boulder at the beginning of the form, because almost every small drumlin starts with a well visible, relatively large boulder. And pictures A and B shows examples flutes with and without boulder. The picture C shows small drumlin with a large boulder at the beginning. And as you can see, flutes characterized with a higher elongation ratio, and small drumlin is much wider. Our flutes and small drumlins are in windy glacier foreland, especially in the west part at the flute moraine, or all are very close to the front of the glacier on area deglaciated after 2006, so they are very young landforms. A large amount of subglacial elongated landforms means that the front of windy glacier is soft-bedded, and the formations of the glacial bed goes very easily. And my conclusions: photogrammetric survey over windy glacier foreland and Red Hill allowed for elaboration of a high-resolution orthophoto map and digital elevation model. And the PW Zoom fixed-wing unmanned aerial vehicle and beyond visual line of sight operation proved us gathering valuable geomorphological information in location distant from the polar station. It's possible due image processing, including to use a structure from motion algorithm and photo interpretation. And its main disadvantage is dependence on weather conditions, and it could be problematic in windy places like King George Island, but in this situation, PW Zoom did it well. And thank you for your attention.
Yeah, thank you very much. Good afternoon. And first of all, I want to thank you all for this opportunity to take part in this event. Can you see my presentation?
Yes, you can see and you can hear you loud and clear.
Okay. I want to present our study, Paleohydrological extreme events in the river valleys of the East European plain, and it is a study of the collective of authors. First of all, I worked with Andrei Panin, and of course this data was got with the help of many people. The relics of large meandering paleochannels or macromeanders are found in the river valleys of the East European plain, and channel widths of macromeanders are few times, sometimes up to 10 times larger than the recent meanders of the same rivers, and large macromeanders are spread globally in the temperate climate zone of the Northern Hemisphere. However, the East European plain is characterized by a great number of such paleochannels and their good preservation in topography of river valleys. So large paleochannels were formed throughout the periglacial zone of last glaciation, and these periglacial rivers were formed under conditions of high spring runoff. And formation of large paleochannels is usually associated with late glacial, the end of marine isotope stage 2. However, there are some evidences of formation of such landforms in earlier times in MIS3. So we studied a few key sites in Don and Volga river basins. It is Upper Don River Valley in Tula region, Khapur and Vorona river valleys in Voronezh region, Savala river valley in Tambov region, and Moksha river valley downstream Snar river inflow in Ryazan region. On these key sites, rivers have wide floodplains with big paleochannels on their surface, which was the main subject of our study. And these paleochannels are the signs of high flood activity epochs. The main aim of our study, main aims of our study were reconstruction of late Pleistocene history of river valleys development, establishment of absolute chronology of large paleochannels formation, and periodization of the phase of extremely high river flow in river valleys of the East European plain. In our research, we used a number of field and laboratory methods, hand and mechanical coring, examination of natural exposures, topographic profiling, radiocarbon and oil cell dating, spore pollen, grain size analysis, and microscopic study of quartz grains. And we reconstructed fluvial chronology of late Pleistocene on the region based on the data analysis, and epochs of high floods and macromeanders formation were established. We made geomorphological maps and profiles across the valleys and some big paleochannels. And also we made the reconstructions of mean annual paleo discharges of the studied rivers based on paleochannels parameters. The main results you will see on the following slides. First of all, here you can see the Upper Don River key site. A few big paleochannels are located on the upper floodplain level, and we analyzed morphology and composition of different alluvial surfaces and the profile across the valley by the line AB. Shows the structure of high floodplain and some of the macromeanders. Dates about 35,000 years BP are found on the different levels, and it can be interpreted as the evidence of river incision at this time. And the most reliable date is this one, about 33,000 years. It is well consistent with the other oil cell date, but in aquatic environment, oil cell dates are often poorly illuminated. That's why some dates can be older, and we think that they are older than they are really is. So All the dates that you see in this presentation are calibrated using Oxcal program. The other group of dates, about 18-20,000 years BP, correspond to the time of macromeanders formation. From these dates, the most reliable one is this one, about 18,000 years BP. Two other dates are a little bit older and less accurate because they were made by total organic carbon. So the first stage of macromeanders formation, as we interpret our data, is between 17 and 19,000 years BP. One more group of dates represents the second stage of macromeanders formation epoch, about 13-15,000 years BP. The most representative dates are these two dates from this borehole, and some other younger dates, for example, like this, correlate to the time of the paleochannel siltation. From the foregoing, we can conclude that big paleochannels formed in the end of marine isotope stage 2 and the epoch of macromeanders formation and high floods presumably was divided into two stages, 17-19 and 13-15,000 years BP, and was interrupted by epoch of lava runoff. The other key site is located in Upper River Valley. Two generations of big paleochannels also were found on the upper floodplain level. You can see these two generations of paleochannels have different size, and we expect them to be different age. The profile by line ABCD shows the structure of few terrace levels, high floodplain, and some of macromeanders. So if we look closer on this profile, we can see the following. Date about 33-36,000 years BP correspond to the time of the first terrace formation. This terrace is about 16 meters above the water level of the Upper River. Another group of dates, about 24,000 years BP, is found a few meters deeper than the modern river level. From that, we can conclude that the river incision was before LGM time, between 25 and 35,000 years BP. One more important group of dates corresponds to the time of the Aeolian processes activation, about 23,000 years BP. It was LGM time, and so at this time river was in size deeper than the modern level. The runoff was very low, and the conditions were cold and dry, and that led to activation of Aeolian processes and formation of Aeolian covers and aprons in the valley. You can see Aeolian sands cover different levels of alluvial surfaces in the Upper River Valley, and Aeolian origin of these sediments is confirmed by the thin Aeolian stratification of these sands and microscopic study of quartz grains from these sediments. After LGM, the high runoff epoch started. That was the time of large meandering paleochannels formation, and first generation of macromeanders is well preserved on the right bank of the modern Upper River. These paleochannels are bigger in size than second generation, and they are dated also 17,000–19,000 years BP. Second generation of macromeanders is most representative on the left bank of the modern Kacper River, and dating of these paleochannels shows the age about 11–13,000 years BP. This data was received by Andrei Panin and courses a few years ago, and in 2019 we continued the study of paleochannels, near Mazurka. So we hope to receive the new dates that can help us to be sure about the age of these paleochannels, because some old dates from Mazurka paleochannels seem for us not very clear and too young. Also, most of previous data is from paleochannel infilling, not from the channel alluvium. These old dates were received by regular radiocarbon dating, and now we are going to use IMS dating and hope to receive more accurate data. Our data shows that epoch of high floods was interrupted by a short Lauranov period in this valley too, about 15–16,000 years BP, when Aeolian processes revoked some of sand surfaces in the valley. For example, Aeolian sands of this time found on the levels of modern floodplain in boreholes TN3 and TN2, and that indicates Lauranov and dry period at this time. So the late Pleistocene epoch of high floods in Kacper River Valley also had two periods, about 1719 and 12 or 11 to 15,000 years BP, like it was previously established in Upper Don River Valley. The characteristics feature of the Holocene was a lowering of runoff and reduction of the meandering belt of the rivers. The same morphology of the river valleys was detected in Varona and Savala river valleys. Here you can see a number of large meandering channels with parameters much bigger than the modern ones, but unfortunately we didn't receive the dates from these two valleys, but we expect the dating would show the same results. The high runoff period and macromeanders formation in these valleys should be at the same time with Kacper and Don rivers. Here you can see one more studied key site in the Moksha River Valley, also with big paleochannels and wide floodplain. And this is the geomorphological map of the Moksha River floodplain. And if we stop on the composition of paleochannels, we will see the following dates: about 30–35,000 years BP from boreholes are found also on different levels, and we interpret it as an evidence of river incision at this time. So the river was incised more than 12 meters lower than the modern channel, and then about 30,000 years BP or later, accumulations in the river valley started, and the most intensive accumulation took place at LGM time, about 20–23,000 years BP. As we already discussed, in some valleys, the evidences of Aeolian accumulation in river valleys were found, but such Aeolian covers we didn't found in Moksha River Valley yet, but we expect that they should be there too. Another group of dates, about 18–19,000 years BP, correspond to the time of macromeanders formation, and you can see that macromeanders of the Moksha River were not very deep, and the river incision at this time was not as deep as it was before in the period between 13 and 35,000 years BP. And we expected macromeanders to be deeper than our data showed. So that's why in the other boreholes we didn't analyze the highest parts of the valley infilling. So we did not date all the macromeanders we expected to. But now we know the depths of these paleo channels, so we are going to fix this flow by dating other macromeanders on this key site to be sure that our interpretation is correct. We have not found the evidences of two periods of macromeanders formation in Moksha River Valley, as we previously detected in Upper Don and Hopper River valleys. But we can suppose that if we have more detailed data from Moksha River, two periods can be found here too. Of course, there could be some local differences in river runoff changes depending on some particular conditions in each place. But in general, the history of river valleys development of the region is the same for all these rivers. For quantitative estimates of late Pleistocene paleo discharges, we used the method developed by Alexei Sidorchuk. The main formulas you can see on this slide. And our quantitative estimates show that late Pleistocene mean annual paleo discharges were from 2 to 4 times higher than the modern ones. A little bit different in different rivers, but few times higher than the modern level. Okay, and just to conclude everything I said, our data analysis shows the following results in all the river valleys we analyzed. The incision of the rivers took place between 30, maybe 25 to 35,000 years BP and was connected with high runoff in the region. So before LGM, rivers were incised deeper than the modern river levels. LGM time, mostly 23,000 years BP, was characterized by low runoff in cryoridic conditions that led to accumulation in river valleys and activation of aeolian processes. In that time, aeolian covers and aprons few meters thick were formed in some of river valleys, mostly on the terraces surfaces. After LGM, epoch of high runoff and macromeanders formation started, which was detected 12 to 19,000 years BP. Also, modern wide floodplains were formed in the studied river valleys at that time. And this high runoff epoch was interrupted in some valleys by low runoff period between 15,000–16,000 years BP. And this time was also characterized by activation of aeolian processes. Some signs of aeolian activity were detected in Hopper River Valley and in Varona River Valley on the levels of modern floodplain. So the late Pleistocene epoch of high floods and macromeanders formation was divided into two periods. And quantitative estimates show that mean annual paleo discharges in this time were a few times higher than the modern ones. And then runoff in Holocene became lower than in late Pleistocene and channel parameters decreased. So the morphology of river valleys and geochronology of sediments indicate contrast in runoff, variations being the characteristic feature of the late Pleistocene. Thank you for your attention.
So, could you see it? Yes, very good. We can see and we can hear you.
Oh, this is really perfect combination. Okay, so I have your presentation with topic Geomorphology of old and abandoned underground slate mines in Nízký Jeseník Upland in Czech Republic. So there is important to say that during the last decade, some segments of the landscape were deeply described and investigated from geomorphological point of view. An important part of subsurface component are caves, especially karst caves. But the geomorphology of non-karst cave is less explored. For example, pseudokarst or abandoned mines. Last 20 to maybe 10-20 years, especially in Europe, cavers are interested in exploring of artificial caves, which means old mines, aqueducts, sewers, and other types, and these voids could host formation that present morphological similar speleothems like in natural caves. My research is interesting about slate mines. You can ask why slate mines. I think that in the world is considerable lack of scientific publication investigating slate as well as slate quarries and mines, and we can say that slate is like something like a forgotten stone. There is important to say that I'm interested about abandoned mines. Here you can see some definition from Unger. And the big problem connected with abandoned mines is that we don't have any documentation. We don't have any information about location of mine, or we don't have any maps and other stuffs. My research is in Nízký Jeseník Upland. It is the biggest geomorphic unit in Czech Republic, which have 2,800 kilometers square. Is situated on the northeastern part of Bohemian Massif, and the rock formations are represented by slates, sandstones, conglomerates, and siltstones. There is really important to say that geological structure is interpreted as thin-skinned accretionary wedge, when we can see that in the all area there is many faults. It is predisposition for creating of mines in this landscape. Mining of slate in Nízký Jeseník have a really long tradition. Wide expansion started in 18th century that was slate mined, especially for roofing purposes. Because slate has never been registered as a reserved mineral deposit under mining law, anyone was allowed to excavate it. During time, slate becoming property of German immigrants because they had the skills for slate mining. But after Second World War, the immigrants was deported back to Germany, and the mines started to be abandoned. Which means that we don't have information about location, map documentation, and other stuff. My research is possible to divide it on several parts, like exploration part, inspection part, mine design, dataset, cracks in motion, and after it, form, processes, and phenomena registered in the mine. Exploration part. We explored around, 167 sites with underground slate mines. Many of these sites was found by Czech Geological Survey from websites. And we found 33 of them thanks to description of local miners or by Tramping Society in Nízký Jeseník. More than 100 new maps were performed thanks to speleological mapping method with using Leica Disto. We visited every site and we explored mine from inside because, inspection part. During our research, we were looking for during our research, we were looking in the mine and for several phenomena, forms, and processes inside. And also we documented, for example, a number of entrances and levels in mine, vertical horizontal diversity, existence of fillings, collapsing, presence of water stream and body, artificial objects, waste, and presence crystals and karstic features. We usually wrote no name of mine, type of mine, because in Nízký Jeseník was mined also of silver in different types of mines, and location. Then we made structure measurement by compass, and we wrote who made the map and thanks by method. Mine design. In Nízký Jeseník, or especially here, there is a really special mining method called the Rhenish mining method. It is a system of rooms situated parallel to heading. We divided mine to 3 groups on small mines, medium mines, and large mines. Many of small mines are only exploration edits, which have only several meters, and the smallest edit have only 2 meters in Nízký Jeseník. The medium and large mines are more complicated and branched. They have several types of entrances. Here you can see on these pictures, for example, we have here inclined shaft, vertical shaft, or classic horizontal edit. And the big mines, they usually have 2 and more levels. In big mines, you can see that there are big chambers, which has many of 10 meters. They are connected between them by branched edits. And on the right side, there is a typical picture of prospection edit, which have only several meters. What is really interesting about slate mines is that in multi-level mines, especially in edit, you can see that they used fillings for building they used fillings for backfilling. Then they used, for example, like arch ceiling or ceilings from on the one side. And fillings have 2 reasons. First was for stabilization of walls, for example, for rooms or some different levels, because they used from fillings, for example, shaft and or some rooms. And also in the mine, you have a typical edit in rock mass. Okay, we made a really big data set. Our research was from 2016 to 2020, so it is 4 years, and we made a really huge data set where we have 167 mines. There is one example how we did it. In this data set, we have official name, type of mine, location, ID, which is from Czech Geological Survey, measurement by compass, who made map and when, method of mapping, land of mine, and then number of entrance and number of level, but you can see on this color mine. After it, we made special numerical index for things like vertical diversity, horizontal diversity, and other things. And it's index like 0, 1, and 2. It's very simple. It means that, for example, when we have a mine where we don't have any presence of water, for example, water body, there is a numerical index 1. When we have a mine which is partly flooded, we have index 1. And when we have a mine which is completely flooded, we have number 2. We made it because we wanted to make some statistic evaluation. It's still in the progress and it's still in the work. We're using 3 methods. And we found some connections, but we're still waiting for our results. In 5 mines, we also making monitoring of cracks. We have a measurement from April 2017, and last was in July 2020. we're using NGM deformatory tool, and we measure different types of motions like subsidence, creep, cracking fillings, freeze weathering, exfoliation, gravitational motion, interlayer motion, and other stuff. For calculation, we used root mean square error with confidence coefficient number 3, which is the best for measurements without dependent control. I think that the most interesting is the Soudek and Kolkochov mine, where are movements around centimeters. For example, in Kolkochov, there is moving 4 centimeters by freeze weathering, and in Soudek is motion 3 centimeters by crack, because in Soudek was localized that there was a big collapse of room, and this crack is in connection with this room. So it's still in the motion. After it, we made detailed petrographic and mineralogical research in the mines, because there is a very important of composition quartz and ferrosilicates in the slates, because thanks to them it's possible to produce tiles that could be used as a roofing material. And in Nízký Jeseník is really big Nízký Jeseník is sorry, there was in history really big tectonic motions and this kind of stuff, and sometimes this changing in petrography, like we have a slate, and in some part of mines where we have a philitic slate, which is not so good for making of tiles for roofing material, and it could influence of stability in a mine. I think that is very important that how you look on the mines, because when you are in first time in the mines, you're looking for typical stuff inside, like some artificial objects after mining, or some collapsing, like wooden pillars, or collapsing from walls or ceilings, and it could be for you dangerous or maybe interesting. I don't know. For me, it's very interesting every time. And if you're looking more carefully, then you can see that in the mines are little different things, and they are similar to nature caves, like speleothems from ceilings or from walls. Like there are some cascades of calcite, crystals of gypsum, huge quartz vein on the walls. Really rich mineralogy here. And if you look more to the detail, then you can see similar forms and processes like on the surface, and some evidence from paleo currents on the walls, or luminization of calcite. There is creating new minerals, and you can see here moon milk, or some forms created by gravitational processes or fluvial processes. As a result, we made this table where we made 3 categories divided according to temporal relation to historical mining events. We made pregenetic, syngenetic, and postgenetic forms, processes, and phenomena inside. And also we divided geomorphic forms according to their relative size on macro, meso, and micro. Also, we just thinking which forms, processes could be permanent or permanent with uncertain future, of which are rare or brittle. We documented collapsing in 31% of mine. I think that the most stable are small mines, because they are only prospective edits which are not branched, so they are more stable. and the most tendency to collapse is in big mines. 90% big mines are in the collapse. After that, we found in 22% of mines mineralization, and in the same mines is there typical karst features like karst tablelands, around 70%. 10% of mines have a water stream, 42% have a water body, and only 80% was largely flooded, like completely flooded. In this research, we're trying to look on the mine like on a big geomorphic system, where you can find connection with every process, form, and phenomena inside. We can look it on something similar to fluvial geosystem on surface or different geosystems in the world, and still there is a lack of information, a lack of publication about this point of view, and I think that it could be really interesting if we look on this like on something similar to natural cave. Not looking on this like on danger, but on something would have our life. That's all. Thank you for your attention.
Good afternoon, everybody. I will turn the camera off just in case I'm not sure if the connection is okay. I will talk about study of the formations in karst caves in Carpato-Balkanites in East Serbia as a tool in seismic hazard assessment. Why is this important in this area? If we see the maps of seismicity of the Balkan Peninsula, we can see that the most of the seismicity here in the Balkan Peninsula is actually released along the contact of the Adriatic plate and the Dinarids, and the most recent earthquakes that were in near Zagreb, near Petrinja in Croatia, and several days ago, yesterday, in Greece, actually tells us that this contact is still very, very active. But of course, seismic activity and tectonic activity is also happening in the inner part of the continent. And if we see here on the map of instrumental recorded and historical earthquakes with magnitude higher than 5.5, which is actually a lot, we can see that there are some earthquakes also in the inner part of the continent, especially in central Serbia, along the contact of the Dinaric origin, which is located in the western part, and the Carpato-Balkan origin, which is located in the eastern part of the peninsula. And so why can't we just study earthquakes and make this kind of map, this kind of seismic hazard map? It's okay when you have a lot of earthquakes and a lot of big, large earthquakes to make seismic hazard maps based just on the study of earthquakes. But when you have small earthquakes and not so big number of them in your area, like we do in Serbia, we have to study some other parts of the seismic process and the tectonic process in order to make the seismic hazard map. If you see this map of seismic hazard in the area of Europe, which was made during the SHARE project in some 15 years ago, you can see that this area of Central Balkan Peninsula is actually very hazardous upon earthquakes. So it's important to study earthquakes and seismic hazard also in this area, even if we do not have so large earthquakes like in the part where the Adriatic plate and the Dinarids are colliding. If we see the map of the regional seismicity, here you have also the map of the Balkan Peninsula and the Apennine Peninsula. You can see main deformational fronts, and our research area is located somewhere here in the eastern part of the Carpato-Balkanites. We can see that in this area also there are a number of earthquakes with magnitude more than 3.5, and we don't know a lot about them because the most we know is about is related to the focal mechanisms, but unfortunately we don't have any fault catalog or something that we can say which fault was active during these earthquakes. Reasons for that are different, but the most of the reasons are related to the fact that there are no so much these large earthquakes, these higher magnitude earthquakes, so we can't tell from the focal mechanisms which fault was active. Because of that, we first what we did surface analysis in this area. This area here, you have the tectonic map after Schmidt et al. And you can see here that this area is located near the contact of this Carpato-Balkan origin with the Dinaric origin along the central axis of the Balkan Peninsula. And here we can see high resolution tectonic map. We see that this Carpato-Balkan origin is actually made up of several trusts that are east vergent and that carry the limestones, Jurassic limestones, which are good for karst caves formations in this area. So in this area, we first did the power stress analysis, standard structural geological mapping on the field using fault criteria, fault kinematics criteria. All we could see on the surface. We made mapping for, I don't know, 3 years or something, and we had about 4,000 data to use in this power stress analysis. And based on that, we divided these deformations in two main deformational phases. The first deformational phase was related to the rotation of this tectonic unit of the Carpato-Balkanites, which is called the Dacia mega unit. And this unit rotated in clockwise direction, and because of that, a large strike slip faults formed. And here, if you see the schematic sketch of this deformational phase D1, you can see that we suppose that this is actually all these faults that are activated during this phase was actually related just to this strike slip component of this large faults in Carpato-Balkanites and the Southern Carpathians in Romania. Some of these faults are well known as Timok fault or Černažiju fault, or other faults that are on almost all tectonic maps of Balkan Peninsula, and the structures that are secondary and that are related to these strike slip movements. And after that, the second deformational phase, which we suppose that it's still active, was actually also strike slip, but is related to the deformation or the activation of the so-called, I called it the locked area, because there is no more room for the activation of large reverse faults, but still the strike slip component is very active. And you can see here in this sketch that we suppose, based on field data, that sigma 1 axis, or the maximum compressional axis, is oriented generally north-south, and the extensional axis is generally oriented east-west. So when we had this data, we then started to explore faults inside caves, and we started with one of the most famous tectonically active cave in eastern Serbia. This cave is located in the southern part of this area, which I showed on the map. And if we see the cave walls projected on the surface map, on surface geological map, we can see that the orientation of the cave itself generally is northwest southeast. Fortunately for us, some 15 years ago and last year, there were some earthquakes in that area. Fortunately, not so large earthquakes, not so large magnitude. And we solved the focal mechanism of this earthquake that happened in 2006. And if we see this focal mechanism, we can see that also one of the nodal planes on this mechanism is also oriented northwest southeast, and based on that, we can see that this the fault, if it is the fault, it should be left lateral fault based on this focal mechanism. So when I started to be a speleologist and to go to caves, first of all, I looked at this cave in order to see if there is something interesting related to this tectonic activity, the recent tectonic activity. So the cave, as you can see on this map, is located in the Upper Jurassic limestones. These are massive limestones, and in eastern Serbia, well known as the best hosting for karst caves. This cave, it's called Mala Bizdanja, is actually near a horizontal cave with the vertical entrance. It has 3 levels, and some of these levels are made up along faults, and we can see this also when we enter the cave. Of course, as I expected, we found a lot of indicators of new tectonic activity in the cave. Some of these I will show in the next slides. These are faulted skeletons like in the picture here, or here we can see shear joints made up in skeletons. Then what we also saw, we saw fault surfaces that cut the skeletons, like here in the image to the left. It's fault surface when we can actually measure striations to see what was the kinematics on that fault. And then on the picture to the right of the slide, also fault surface cutting the skeletons, and because of the most probably the seismic activity, some part of the skeletons gravitationally fallen down. There are also a lot of examples of faulted cave columns and faults or shear joints which cut the skeletons, like on the picture to the right. And also what was interesting is that we also see faults that cut skeletons that incorporates an older skeleton. So these examples can show us, actually can be good examples if we wanted to do dating, absolute dating of the fault activity inside this cave. Also, what was interesting is that we found a lot of examples where we can see fault gorge that was formed because of the fault activity, and inside that fault gorge we have clasts that were made up of skeletons. So it says us that these faults, activity of these faults should be neotectonic and should be, of course, younger than the formation of these skeletons. This was also a good example that we have faulted limestone, actually column of limestone, the host rock inside the cave, but in the fault gorge we also have clasts that incorporate these clasts actually is made up of skeletons. Also, in the picture here we can see that there is small clasts that are also made of skeletons that are located in this fault gorge that also have clasts of the host rock of the limestones. Also, what we saw in this cave is that we can clearly see the reverse faults, the reverse left lateral fault actually, not with the pure reverse component, which belong to the fault system that is controlling the speleogenesis of this cave, and we could clearly see the striations, like here on this image or here on this image, which shows us kinematics of this fault. But also, how do we know that this fault is probably tectonically active? Is that here in this part here, in the upper part, we have also fault gorge that incorporates older skeletons, so it should be younger than the skeletons that were formed in this cave. And what we know about the age of these deformations, unfortunately not a lot, because we haven't done some radiometric measurements, because what we done up to now is just mapping, structural mapping inside this cave, but we will take samples to do radiometric measurements of these skeletons. But what we know is that we have several generations of the skeletons, and here is a good example that skeleton is forming along, over an already faulted older skeleton. So we know that these faults are younger than the skeletons, but we need to date first skeletons to see which is the fault activity. And what we still want to see here and to do inside this cave is to map all these faults and to try to see to calculate actually the fault slip rate and to use these fault slip rates in seismic hazard assessment as a first order data for seismic hazard calculations. And this work here in this area is also of high importance for the active tectonics of the Balkan Peninsula, because in this area we know from previous studies, our previous studies and other previous studies, that there is a slight change in stress rate here in these Carpato-Balkanites, because here in this central part where we do our research, it's strike slip. I'm sorry, but as we go up to Romania, to Southern Carpathians, we have some extensional components. So we are trying now to map, to do structural mapping in this white rectangle in the whole eastern Serbia Carpato-Balkanites to see first to map faults, active faults, and then to try to calculate fault slip rates, and then to see if we can use this data and how we can use this data to calculate seismic hazard better than just by using already happened earthquakes in this area. That was all. Thank you for your attention.
Good afternoon. I would like to express my thanks to this fascinating and fantastic event. And I would like to thank all organizers of this International Geomorphology Week. And I would like to have a talk about geomorphological and geological causes of natural hazards in the Ukrainian Carpathians. And I would like to describe the natural hazards in Ukraine in general, and I would like to talk about geological risk and hazards and the main causes of many processes, and the principles and method of the assessment of the impact of these processes on infrastructure objects in the Carpathians, and special techniques for this assessment. As you know, Ukraine has a lot of natural hazard processes, and these natural hazards pose serious problems. And for example, in 2019, there were more than 150 emergency situations in Ukraine, and most of them had the geomorphological and geological causes. I would like to say that according to mechanism and of the impact of geological media and geomorphological factors, following types of this impact can be distinguished. First of all, it's physical, caused by energy transfer from physical fields, physical chemical impact related to different properties of rocks and the interaction between components of natural and man-made systems, and the chemical impact related to the chemical and biological interrelation between different components of the man-made system and natural systems. And principal phenomena and agents constituting these impacts of various nature are respectively gravitational, mostly mass movements, hydrodynamic, physical, chemical, and biological factors. And I would like to say that among a very big processes and phenomena related to existence of different infrastructure objects, we pay attention on that can result in major changes in the infrastructure and unfortunately cause many catastrophic events and many accidents. I would like to say that we can describe the many causes and the many factors of natural hazards, and they could be described by different processes and different rheological models of elastic, plastic, and viscous medium. There are a lot of natural hazards in Ukraine. First of all, it's floods, and this year we unfortunately we had a lot of accidents in the summer. Most of houses were destroyed and damaged, and a lot of people suffer from this flooding, unfortunately. The total number of karst processes is 22,000, and in Carpathians, these processes are related to neogene molasse formation, and these rocks have a general northwest-based strike, and they are characterized by salt, mostly salt layers. The landslide hazards are the big hazards in Ukraine, and as you can see, there are more than 22,000 of landslide in Ukraine, and cover big areas in different parts of Ukraine. You can see the distribution of landslide is related to geological structure, and unfortunately we have a lot of accidents due to landslide hazards in different parts of Ukraine, in Carpathians, in Kiev, on the coast of the Black Sea, and the distribution of the debris flow in the Carpathians is due to peculiarities of tectonic, seismic regime, and depends on geological and geomorphological factors. And in the Carpathians, the debris flow occupy more than 40% of the area. Of course, we have the seismic events, and more than 20% of Ukraine is located in the seismically dangerous areas. Carpathians, Ukrainian Carpathians are characterized by active formation of different natural hazards processes, including landslide, debris flow, floods, and so on. And we have a big number of landslides of this area. And that's why the database of many landslides have been developed with different parameters of landslides, and to study the different causes of landslide activity in the Carpathians. The susceptibility model have been developed, and it includes different layers and factors, including hydrogeological, structural, tectonic, bedrock, and so on. And we used the special approach to the susceptibility modeling of landslide hazards, and it includes the relationship between each factor of landslide activity and distribution and the occurrence of the past and present landslide. And geomorphological and geological factors like seismicity, tectonics, slope, climate, and others have been considered. And 5 categories of these methods are identified by, first of all, geomorphological mapping, analysis of inventory, statistical method, and conceptual models. And a couple of words of the main factors of natural hazards in the Ukrainian Carpathians. First of all, it's a lithology and stratigraphy of rocks, and I would like to say that most of the landslides is related to the flysch deposits, and as you can see, this area has 2 structural maps, and the lower structural layer is formed by Carpathian belt, and these sediments are presented by mostly flysch formation. The special field study determined the composition and structure of many landslides, and in the Carpathians we can see predominantly the structural landslides which formed in homogeneous anisotropic environment. Special field study determined the special role of destructive zone, of weak zone of flysch deposits with different orientation relating to slope and valleys. And this destructive zone, this weak zone of flysch deposits are characterized by intense glaciation, fraction, stratification of flysch deposits, and you can see on this map that many of landslides are related to this zones which have the different orientation to the river valleys. We did a lot of special field research and tried to find the the correlation between the landslide processes and tectonic and structural factor. And one more time, we prove that there is a big correlation between the structural weak zones and the formation of landslides in the Carpathians. The GIS modeling and distance analysis prove these relations, and it was proved that many landslides are related to the different types of fault zones in this area. Of course, the geomorphological factors are the main factor of landslide hazards in the Carpathians, and it was proved that the most of landslides occur on the slopes of the 20 to 35 degree, and the development of the digital elevation models and some maps determine the presence of the landslides and their relation to the geomorphological factors. And it was proved that the present and neotectonic movements had a big impact on the landslide formation, and structural morphometric analysis has been used for the assessment of the impact of this factor on the landslide formation, and we try to assess the amplitude of the neotectonic movements and the general trend of this movement in the Carpathian mountains. And of course, the impact of seismicity on the formation of the landslide processes has been proved. We try to analyze the different data for historic data, for historic period and instrumentation records, and it was proved that each seismic shock can be moved to the unstabilized each landslides for 5 millimeters. We try to use this special GIS modeling for the ranking of each factor, and try to make a factor of weight analysis to define the impact of each factor on the landslide formation. And finally, we have the susceptibility map of the landslide formation in this area. But I would like to say that it was the general impact of different causes on the landslide formation to know the genesis and the dynamic of each landslide. We have to use the different methods, including geophysical methods, remote sensing, of course, and some infrared thermography method, and to know the zones of high water saturation, to assess the many weak zones and the special elements of the landslide. We use the electrotomography. It was this year in the Carpathians, and this helped us to assess this and to find the different elements of the landslide body, and to know the depth of the surface of rupture of the landslides. And of course, we try to use the drone images for the assessment of the morphometry and calculate some elements of the active landslides in the Carpathians, which happened this year and caused any damages in this area. And infrared thermography can be used for the assessment of landslide activity and for the assessment of potential landslide activity in this area. We try to investigate the shallow landslides by using the ground penetrating radar, and this can help us to evaluate the thickness of the landslide body, stratigraphy, and incline of the some layers. And for the local prediction of landslides, the calculation of the landslide stability and stress strain state of the landslide prone slope help us to define the zone of the potential landslide activity within the landslide prone slopes. In the Carpathians, it was used different equations, and we developed the special models that allowed us to assess the landslide, potential landslide hazards depending on the different parameters of slope and physical mechanical parameters of rocks. And debris flow hazards in the Carpathians has a great impact on the community of this area, and the main causes of the debris flow are the presence of the flysch deposits and destruction products, which could be a solid phase of the debris flow, the heavy precipitation and the heavy rains in this area, and it happened this year too, and of course the landforms and present movements. And I would like to say that the 40% of the area of Carpathians has the debris flow hazards, and there are 400 debris flow basins in the Carpathians, and field and analytical research proved they occur each 20-25 years, and unfortunately caused a lot of damages in this area. And we did a lot of field research of debris flows in November of 2020, and most of people suffer from debris flow hazards in this area. And to calculate the potential of debris flow hazards, the algorithm and special software have been developed. It's based on the empirical data of the Carpathians, fundamental hydrodynamic laws, and Bernoulli equation, and it helped us to calculate the hydrodynamic force and the impact of debris flow on infrastructure in different areas in the Carpathians. The same calculation and this similar software has been developed for the assessment of flow impact on the pipelines in this area, and the classification of different types of flows has been developed, and it helps us to assess the impact of the different types of flow on the infrastructure in the Carpathians, and use a lot of hydrodynamic formulas and laws for the assessment of this impact on different types of infrastructure in the Carpathians, and special software has been developed for this assessment. And I would like to say the result of this research, of course, can be used for different risk assessment, assessment of natural hazards in the Carpathian, and could be used for infrastructure planning in this area. And I would like to invite all of you to third EEG workshop on assessment of landslide hazards and impact on communities. It will be held this year in Odessa, in the south, on the south of Ukraine. But first a workshop we organized in the Carpathians, and it was a very, very good field trip with the assessment and study of the natural hazards in the Carpathians. Thank you very much for your attention.
Okay. So I will go to the next slide now. Okay, so small introduction to the topic with which you are maybe familiar with, about the chemical denudation, which was main aim of the study in the many karst areas of the world in the last decades, I would say maybe last 50, 70 years very exactly. Because the chemical denudation and evolution of the karst relief is the one of the basic processes of the karst formation. In this chemical denudation, it is very important to take into the consideration many different physical, geographical and geological conditions. So this is why the chemical denudation is, or the rate is so different in different climate conditions, in different CO2 amount of the soil, in different soil types with the different chemical reaction of the soil or rock properties and so on. So like I said, it was a part of the research or typical karst research, classical one, in various karst areas of many decades. And we started to do some, I would say, preliminary research of the area of the Slovak karst by this way. After the starting of the cooperation between the IRCK Gwilym, Karst Research Institute in China, and between our research institute in Košice in Slovakia. At the beginning, it was very testing how it's going to be working, if we have some results, if we can to do this further, and I will present some small results of this now. At the beginning, I would like to present small hypothesis of the topic, why we started to do this in this area exactly, and why on these experimental sites exactly. For us was, or it is from the geomorphological point of view, very interesting information and question which is still not solved, why the western part of the Slovak karst area is much more developed from the geomorphological point of view in the when we are going to have a look on the eastern part. So there were many theories in the last years, or last maybe 30 years, which were talking about sedimentation of the area in the east, or about the dolomitization of the limestone in this area. And we were also thinking about the lower dissolution rate here because of the quality of the limestone in the eastern part. I will show you on another slide the chemical analysis of this. This was the most important hypothesis. Then on the other hand, there was another study from the year 2010, which was the first one in this part of the Slovakia on these limestone tablets also, exactly on the same plateau where we are conducting our research also. And also we were interested in some significant seasonal changes. So these were three main points why we started to do this. So after some first thinking, we set up two experimental sites, which one is in the western part and one is in the eastern part of the Slovak karst. We started to do some measurements, preliminary measurements, to have first data, to have a look on this. And we wanted to compare our results with another one from the Slovak karst, but also from the Slovak Paradise, which is another plateau karst area, which is only around 80 kilometers to the north from the Slovak karst area. Our research is based on the idea of GAMS. Everyone who is working somehow with the karst knows him and his publications. And he also started to do really huge cooperation between different or many geomorphologists all over the world. There were more than 40 contributors from Asia, from US, from Australia, from Europe, and so on, which starting to use standard tablets from the limestones. And these standard tablets were made by Gams and his colleagues and sent to all these countries. So everyone was using these limestone tablets from like a standard. I will use the word standard in this presentation, which are originating in the limestone from Slovenia near the city Lipica. And the main aim of his study was somehow to collect data as much as possible from different climate regions, different soil types, and also from different positions from the surface, buried in the soil, in different depths in the soil, in different vegetation areas. So they were prepared small study areas like this on the picture on the right side. This is from Grimes, which was published in GAMS from 1981. Like you can see, there were some tablets which were hanging in the air, mainly, or the most of them were around 100 centimeters or 150 centimeters above the surface. Then some of them were put on the karst surface, and some of them were buried in the soil between minus 10 centimeters to minus 60 centimeters. So this research was ongoing quite a long time, around 4 years. These results were also published in more reports and papers. So first idea or first view on the Slovak karst area. So this is Slovakia, like you see. Slovak karst area is situated on the south of the Slovakia, on the south boundary to Hungary. It's a region which is around 800 square kilometers big and extends into the northern Hungary, like Aggtelek karst area. So this area is only divided by the historical state boundary between these countries. So in the middle of the plateaus, I would say. Maybe some better view on this 3D model of the area with some photos to explain how the area looks like. Like you see, we have some separated plateaus. These plateaus are divided by deep canyons. The difference between the plateau surface and the surface or bottom of the canyon is around 400 meters. The same in the east part of the Slovak karst, where deep gorges are cut into the surface. And like you see on the 3D models, all these points or depressions in the western part of the Slovak karst are deltaics. So we have very huge density in the western part, around 50 to 60 deltaics per square kilometers. But on the in the eastern part of the Slovakia, we have only Slovak karst, we have only around 5 to 10 deltaics per square kilometer. So this was this main hypothesis or main idea why to put these experimental sites in the different part of the Slovak karst. This is very simple geological cut of the Western Carpathians. This is the part where the Slovak karst situated is. So you can see this is like a complex of the tectonical units. And on the geological cut, we can find from the non-karstic bottom naps, which are from lower Triassic to the very good karstified Silicicum nape rocks, which are from the Mesozoicum time. Again, very simple geological map in the scale 1 to 50,000. All this violet color are limestones, different types, but mainly Wetterstein limestones. These are very pure and very good karstified, so they allow very good evolution of this karst area in the past and also in the present. On the rounds of the karst, not only in the eastern part you see, but also in the western part of the Slovak karst, are some very thick position of the quaternary sediments, which are called polter sediments. So we are going to our experimental localities. The red dots are experimental signs of the west and east part of the Slovak karst. Both of them are or were set up in the very similar natural conditions. That was very important for us to have comparable results from the analysis or from the measurements. So both of them are around 500 to 570 meters above the sea level on the flat surface, with the rainfall around 600 to 800 millimeters a year, with the evapotranspiration between 400 to 600 millimeters a year, with the a soil reaction which is neutral to the 8 pH. But this is very different in different periods of the year also. Both of these soil types are Renzina, and both these localities are in the beech oak forest. So they are not in the open area without high vegetation, but both of them are in the forest or situated in the forest. Some words about the methodology. So we have 2 sets of the limestone plates on both localities. We wanted to avoid the deviation due to heterogeneity of tablets, or maybe due to some mistakes or some accidents by transport or something like this. So we put one set which we are calling standard plates, which we got from the IRCK in China. We put them or dig into the soil at the end of the year 2016. So in this study, I'm presenting dissolution rate or denudation rate from the almost 1,500 days. And after that, we decided to construct and put the next set of the tablets, which are from the local limestone. We put them in the middle of the year 2018. So now we have on each location or experimental site 3 tablets on the surface from the standard, and 3 from the local, and also in the depth of the soil of 20 centimeters are 3 from the standard and 3 from local, and also in the depth of minus 50 centimeters. So together on each site are in total 18 tablets. To have better data or more data because of some potential mistakes. These plates are excavated each 3 months from the soil. They are very quickly dried in the dryer in the laboratory. So every 3 months are going some people, I would say, into the field. They are digging out very carefully these plates. They are put it into special boxes not to damage them by the transport. They are driving to Košice. It's around 150 kilometers. After that, they are dried 8 hours in the laboratory. Then we are going to weigh them very quickly because of humidity changes on the plates or on the tablets. And again, buried it in the soil. So this whole action is around 2 days every 3 months. So you are digging out at the end of the March, June, September, and December. And like I told, there is drying in the oven in the laboratory for 8 hours by 80 degrees, and waiting by precise weight in the laboratory. We were using at the beginning the Mettler Toledo with this precise. We also done some chemical analysis where the plates were milled on the vibratory mill and analyzed by atomic absorption spectrometer. And after that, this measured data we were counting by this formula for a dissolution rate, which is consisting of the weight at the beginning of the measurement after the 3 months. The time, the days, how many is the plate buried in the soil, Then here 365 days a year, and because we want to have it in the square centimeters, it's the how many square centimeters is the surface of the tablet. So here are some pictures from the tablet which were constructed on the institute from local limestone.
You have 5 minutes, Alena.
Okay, so I'm going very quickly. So these are these standard tablets. You see 97% of CaCO3, so very good quality of the limestone. On the another side, we have these local tablets, which have also quite good quality. On the eastern part, the quality of the limestone is a little bit worse. It's because of the composition of silicates, probably, which are not soluble, so almost 10%. So here are our results from the area. Like you see, we have, I'm comparing standard and the local plates. You see there are quite big differences. Another thing is that the local plates are not so long time in the soil like the standard one. So I would say that after the same day of the exposure, the results will be very similar. And here are the depths. So if you have a look on the western part and eastern part, in the eastern part of the Slovak karst area is the dissolution rate higher. We were thinking it will be in the western part, but it is a classical, so it's going from the surface to the depth of the soil. Here in the western part, it's not so clear. In the depth of the 20 centimeters is the dissolution rate higher than in the 50 centimeters. But now we can't tell or say why it is like this. Here are some graphs of these results. We see some anomalies here. Here are depths, you can have a look. At the end of the first period of the year 2018, there are some abnormality in the dissolution rate, but I will show in the next slide also why. You can have a look here with the rainfall. So these are these dissolution rates in the Yaso is the eastern part, and the green one is the western part, and the rainfall amount. This is this abnormality which you see. It means that here was much more rainfall that usually is in the first part of the year. Almost double, or I would say between 100 and 130% more than normally. So also the dissolution rate is abnormally in this part of the year. Another seasonal changes which are visible from this graph is, for example, this one. This is July to September. We have quite good amount of the rainfall, but we have also vegetation in the full season. So we see this like the dissolution rate is going down. Again, another type is here. We have a lot of rainfall, but less vegetation season. So you see that the dissolution rate is going to the top. This is the last graph which I'm going to show. We have some data from the evaporation, not evapotranspiration, because this is the data which we have from the Slovak Hydrometeorological Institute. the evaporation data are not directly from the area, but the area which is very near to our study area. Evaporation is measured only between the April to September, October. So because of this, still only these two columns. And you see also some abnormality here. Really huge evaporation and also very low rainfall, and because of this is dissolution going very rapid down in this part. This period was very specific. The August was very warm, and also rainfall was very low, minus 20% or 25%. Only to have a look on our results with results from the Slovakia from another part. So we are, I would say, in this result inside, so it's very good. Another thing is directly from the same area of the Slovak karst, this eastern part, Jasov Plateau, there are some results from buried limestone tablets and on the surface, which are very low from another authors. So this is the question, why are these so low? And here you can see another interesting, or for us interesting, regions from the Europe or China, which have really enormous dissolution rate on the surface, and it's going to the down to the depth. So it's a completely different direction. Very short to conclusion from our seasonal changes and from our positions of the tablets. We have lowest dissolution rate on the surface, highest dissolution rate in the soil, low dissolution rate where the rainfall is missing, where also a lot of the rainfall is, but is growing season and higher temperature because of the transpiration and evaporation. We have low dissolution or denudation rate, and high dissolution rate is there where the rainfall is. Also melting snow, this is the next point which we want to do because of the aggressive water. Where the CO2 is better dissolved, like in the normal one. And our factors which we are thinking is the most important for this moderate climate. Really last slide, what's the next? Because this was preliminary result and it was the beginning. So we would like to bury more limestone plates this year under different vegetation conditions. We are going to start measurement of the CO2 and moisture in the soil this year. We would like also to start measurement of the chemical analysis and to get more precise data because of this above mentioned characteristic. We are thinking now about comparison to results from the micro erosion meter, because many authors which are going or which are dealing with the denudation rate are comparing to also these measurements. But what is now ongoing or it's working since 2013 is the research of the denudation based on the hydrochemistry of the karst water. But we have there some small problems with the discharge areas of the springs because it is protected area, and there are some restrictions to use some tracing test and so on. So that's the thing. Thank you very much for your attention, and if you have more remarks or questions, you can also contact me by an email.
Okay, hope you can see the screen now.
Yes, we do. Everything works perfectly.
Okay, so thank you for having me here. It's great pleasure to talk in this session. Hope everyone is awake and not fall asleep in this late afternoon. My talk will be about landslides in the Czech part of the outer Western Carpathians. I will present results of mainly results of our recent study, but also I'll present results older. So that's why I brought a broad team of people here, which are dealing with landslides in the Czech Carpathians. The whole team is led by Tomáš Pánek. So our study area, first aims. I'd like to demonstrate Czech outer Western Carpathians as a landslide hotspot, and I would like to answer questions like what controls distribution of the landslides and deep-seated gravitational slope deformations in the region? How diverse are those landslides? What types of landslides do we have in Czech outer Western Carpathians? Is there any connection between landscape type and landslide mode or landslide type? I will tell you a little bit about timing of the landslides. And at the end, I will show some interesting examples of different landslides. Here I use term landslides as umbrella term for different types of landslides and slope deformations like sucking type or lateral spreading. So don't be confused with this. And when we got LiDAR data for our region, it really changed our view on the topography of outer Western Carpathians, because it revealed us a large number of landslides, and before that we had a landslide inventory made by Czech Geological Survey, and in this inventory they made it in the field and they used topographic maps in scale 1 to 10,000, and they mapped a large number of landslides, but some of them were mapped incorrectly or some of them were missing. So in our study from 2019, we did new mapping based on LiDAR data, and you can see the differences on the figure on the right. So our study area is in the eastern part of the Czech Republic. On the border, it borders with Slovakia and Poland and Austria on the south. And of course, whole region of outer Western Carpathians doesn't end on the border, but it continues to Slovakia and to Poland. But at that time, we had LiDAR data mainly for Czech part. So we mapped all the landslides there, different types, I'll show you later. And in general, the study area was about 7,500 square kilometers large. We had a limited Pleistocene glaciation during Elster and Sal, and it was here in the Piedmont areas. We didn't have any mountain glaciers there. Whole area is typical with low seismicity and relatively high precipitation, but those precipitation varies in the region from 500 to 1,200 millimeters per year. The highest values are in the Moravskoslezské Beskydy Mountains. The area consists of different tectonic units, and we simplified these tectonic units in 6 different units. You can see these units here in the different colors. And these tectonic units have expression in the topography. So the highest part of the Czech part of the outer Western Carpathians is formed by thick-bedded flysch, sandstone-dominated flysch here, Moravskoslezské Beskydy Mountains, and the other areas like Hostýnské vrchy, Javorníky Mountains, Vizovická vrchovina, which is formed by glacial unit. They are composed of flysch which is made of relatively uniform occurrence of sandstones and clay stones. Here on this slide, you can see those differences between those tectonic units. As I said, we have Silesian unit, which forms the highest part, especially the southern part, which forms the highest part of the Czech outer Western Carpathians, is made of those thick-bedded sequences of flysch, and it forms monoclinal structure with steep northern escarpments and relatively gentle, gently dipping southeastern slopes. The internal Magura group of nappes, which is formed by 3 tectonic units, is, as I said before, formed with flysch with uniform occurrence of sandstone and clay stones, and it has a different character in topography. It forms anticline and syncline belts, relatively narrow, and there is nice expression of those sandstone layers in the topography in LiDAR data. Then we have Piedmont areas, Žďánice subsilesian unit, where we have flysch, which is dominated by clay stones and marl stones, intensively folded, and there are also some limestone clippings, and it forms isolated elevations. And the lowest area is are those neogene basins, which are made of marine and fluvial lacustrine clays, sands, gravels, which were slightly uplifted, and they are horizontally bedded. And in these areas, we have broad interflows, dense gullies, and as I said, those slopes are very gentle. So we have a very variable landscape, which is the result of tectonics and lithology. And now I will tell you how this affects the landslides. So on this slide, you can see different types, different examples of landslides we mapped. We mapped Sekung type DSGSDs. This is example from Moravskoslezské Beskydy Mountains, lateral spreading, translational rock slides, rotational rock slides, small debris slides, airflows, and complex landslides, which have part with some rotational component, which then transform to airflow. And here on this map, please have a look on different landslides in those tectonic units. And you can see that it quite differs. Here, for example, in Moravskoslezské Beskydy Mountains, we have a lot of large landslides, translational landslides, but these type of landslides are missing in those in these regions in Hostýnské vrchy, Vizovická vrchovina mountains. In total, we mapped about 13,000 landslides, and 10% of those landslides were larger than 0.1 square kilometer. And in Russia unit, which is the largest tectonic unit, we mapped about 7,400 landslides. But if you compare it with Silesian unit, where we have just 1/3 of the amount of landslides in Russia unit, but the area of landslides is practically the same. So this is just example of how diverse are those units in terms of size of landslides. And in terms of different types of landslides, please have a look on this graph here. About 50% of mapped landslides were classified as debris slide, but this also differs in different tectonic units. In Silesian unit, we have a bit lower amount of debris slides, but we have here relatively large amount of translational slides. And if we compare it with Russia unit, here you can see that translational slides are almost missing. They are in just 3% from the total amount, but here we have large amount of airflows, and the same is in Bystrica unit. Here, large amount of airflows and rotational slides, and some complex landslides. So we did a kernel density map of different type of landslides. Here you can see nicely that if we take all landslides, all 13,000 landslides, we have nice hotspot in Chřibě Mountains, Vizovická vrchovina Mountains, Hostýnské vrchy, and those are those small landslides which occur there. But if we take just those landslides which have area more than 0.1 square kilometer, those landslides occur mostly in the Moravskoslezské Beskydy Mountains, in Bílé Karpaty Mountains, and they are almost absent in this, let's say, central part of our study area. Quite similar it is with deep-seated gravitational slope deformations. This little hotspot relates to lateral spreads in the Neogene basin. For the rock slide, where we have those translational slides and rotational slides, the highest density is again in Moravskoslezské Beskydy Mountains and in Bílé Karpaty Mountains. And it's quite the same pattern with or inverse pattern for the flow type landslides like airflows and complex landslides, which occur mainly in this, let's say, central part of the study area, which is formed by those mainly claystone rich flysch sequences. Here we have a look on a topographic expression of those landslides. On the figure on the right, you can see how distribution of the altitude, local relief, and slope in landslide area and in non-landslide area. And have a look on the large landslides and GSGSDs, as we have here bimodal distribution. Relatively large amount of landslide area is for the large landslides and GSGSDs is in low altitudes and in the local relief, and this is the result of those lateral spreads in neogene basins. And it's quite obvious that whole distribution of altitude, local relief, and slope is in general moved to higher values. If we compare the Silesian unit and the Bystrica unit, the difference between non-landslide area and landslide area is more pronounced in the Silesian unit. And this is because in Silesian unit, as I showed you, we have those translational landslides, which are partially developed. They are resting on the slopes. They travel just a little bit, and they do not form those large accumulation, gently sloping lobes as those airflows or some complex landslides in the Bystrica unit. On the left picture, you can see distribution of or percentage of landslide area in each bin of the morphometric parameter. So, for example, the highest areas, which are mainly in the Silesian unit, they form just a little bit from whole study area, but they are about 40% covered by landslides. If we look on the neogene basin, here we can see that relatively large amount of area is covered by landslide in those low values of local relief and also slope, as was shown in this figure here. So let's have a look on aspect, and here we can see how landslides prefer southern slopes in the Silesian unit, and those are those translational landslides on those cataclinal deep slopes. And I'm running over the time, so I'll move to timing of the landslides. On this map, you can see dated landslides in whole region of Western Carpathians. And if you look on the Czech part of the outer Western Carpathians, we can say that mostly they originated in the Holocene. Some part of the landslides occurred in transition between Pleistocene to Holocene, and then we have relatively large amount of landslides which occurred 1,000, 2,000 years BP. And it relatively corresponds to local wet phases. But we don't have just some prehistoric or ancient landslides here. There was a large amount of landslides during landslide event in 1997. And these are landslides which were mapped and studied by Geomorphology. And here you can see activity of those landslides during the event of 1997.
5 minutes.
Here, okay, yeah. Here is a landslide event from 2010, and Moravskoslezské Beskydy Mountains had the highest amount of precipitation, but as you can see here, the amount of landslides is relatively low in comparison to those areas which were formed by clay stones. This is just a figure which shows the relation between claystone dominated areas and sandstone dominated areas, and this is from the national landslide database, and those red dots are active or recently active landslides, and those gray ones are fossil or stabilized. So it seems that the recent activity is uneven in all the region of Czech outer Western Carpathians. I promised you some examples, but I don't have much time. So Jirova is our largest recent landslide. It has landslide area about 20 hectares, and volume 2 to 3 million cubic meters. Really impressive view. Here is an example of succung type deformation, which disrupts whole mountain, Smrk mountain, second highest mountain in Moravskoslezské Beskydy Mountains, and this succung type deformation was used also by some shallower landslide, which formed on this margin, or on its right lateral margin, very peculiar faults, transpressional faults. The latest example is Pulcini landslide, which has more than 18,000 year long evolution. And to conclude, as I said, Czech outer Western Carpathians are very diverse in terms of lithology, in terms of tectonics, structure, and it affects both landslide density, landslide types, and also density of large landslides. So we have high density of landslides in those short wavelength mountain topography, those anticline belts, where we have airflows, debris slides. In the region with the highest mountains, we have succung type GSGSDs, and on the deep slope, translational rock slides. And in the lower regions, where are isolated hills, we have rotational rock slides, and in neogene basins, we can find spreading type GSGSDs, and in general, the density of the landslides is relatively low there. But in this region, vast number of those landslides were also transformed by intensive human activity. So some parts of, or some landslides are, of course, missing there. So to conclude, I think that with more than 13,000 landslides, and with more than 1,300 landslides larger than 0.1 square kilometers, we can say that this is really a landslide hotspot in Czechia. Large landslides and GSGSDs are also located in low gradient landscape. distribution of large landslides and small, shallower landslides is different, and it's a result of variable topography. There is variable tendency to produce large landslides in different tectonic units. Landslides cluster is concerned with geological conditions and landscape morphology, and the recent landslide activity varies. It seems that claystone dominated areas are more prone to landslides in the present conditions. Here are references, and thank you for your attention.